the analysis in batch offline. Right? So when you come back in the evening, you have 10 water samples, you can run them and you can say, so-and-so sample had this distribution of species in it, and so-and-so other sample had this distribution of species in it. And maybe that governs what you do tomorrow, right? You go out and sample for some other species. And so so over the last 20 years or so, it used to be the case 3 decades ago that human beings went out in boats, took water samples, either using tow nets or using scoops of water, using capsules, and brought them back. It's been fairly common in marine robotics to send vehicles out to do this. But where the vehicle sample is typically all pre-programmed. So people look at data, they hold a team meeting the previous night, they pick certain locations that are likely to be good for certain species of alga they care about, and the vehicle goes off and samples at those locations. Right? And then you come back and check to see if you did okay. So it occurred to us when they were describing this problem that the vehicle is actually capable of making measurements as it's in the water. It can't make on-the-fly measurements of the actual biology, but it can make on-the-fly measurements of the physics and the chemistry of the water. Right? So these vehicles measure what's called environmental context. They measure the temperature, they measure the salinity of the water, they measure the concentration of certain nitrates in the water. They have a full sensing suite that they employ. And so this was joint work with Mbari. This is their vehicle. And the vehicle is equipped with these syringes, which they call gulpers. There's 10 of them. And so the way the vehicle is used right now is somebody pre-programs where each of these syringes should draw water. The vehicle goes out, and when those geolocations are triggered, the syringe will draw water. Right? And then those come back to the lab where manually there's an assay, and that assay produces histograms of this type. So on the x-axis are various species of alga. On the y-axis is their relative abundance. Right? So you get a fingerprint for each place that you gathered water. So what we'd like to be able to do is we'd like to somehow be able to go directly from these measurements that the vehicle can actually make to predicting what the likely fingerprint looks like. Right? And so because this is something that strikes us as something you could do from data, it's not unreasonable to think that maybe you can build some sort of model that allows you to go from these physical and chemical measurements to a prediction of what the biology looks like. And so that's what we tried to do. Because you can see that if you're successful in doing this, then maybe you can trigger good sampling decisions based on the measurements you're actually making. So now the problem is a little bit tricky because it's not a matter of, species A of alga likes to hang out at a particular latitude and longitude. By definition, that can't be because the alga don't like to hang out at any particular location. They're swept along by the water. So there's no simple geographical tag that produces this forward mapping for you, which is often why the kind of manual techniques that oceanographers use fail. They sort of mostly rely today, the state of practice is, location X was hot for this species yesterday, therefore it'll be hot for this species tomorrow, right? Or maybe there's a rudimentary ocean advection model that says that patch of ocean will have moved a little bit during overnight, so let's kind of accommodate that motion and go sample a little bit off to the left or the right, and that's where you'll find this microbe again. And that's kind of what they do right now. But in fact, the location is neither here nor there. What these species really are doing is they're optimizing their abundance. It's largely a function of the chemical and physical environment of the water that they're embedded in, right? So the temperature, the salinity, the food they have available to them, things like that. And those are things you can actually measure in the vehicle, right? And so the question is, can you build a forward model that uses those? So that's what we set out to do. Now, a couple of things about this scenario. It's a kind of peculiar scenario. These sampling decisions are irreversible. So when a syringe opens and you draw water in, you contaminate it. And so there's no notion of saying, oops, and therefore we'll eject the water and sample again. And so you essentially on one run get to take a finite number of water samples. So it's a finite, irreversible sampling problem. Very different than the way computer scientists think about sampling as making measurements. So you can take pictures, you can run out a disk, but often not. You can take a second picture, right? But there's not an undo very often in these things, right? So that's a problem. There are people who work on cleaning syringes and figuring out how to do this better and so on. But for now, for us, this is, you fill the syringe, you're done. So this is the setting, right? So how do you work on this? So here's our workflow for this. We looked at about 10 years of data, which was manually labeled by oceanographers. So people had set sampling locations for their vehicles. They'd gone out, they'd taken water samples, brought those water samples back to the lab, and had done manual labeling of the fingerprints that they'd seen at those locations. So we had paired data for the physical and chemical properties of the water and the associated fingerprint. We use that to build a forward model, and I'll tell you what the model looks like. It's not particularly fancy. But more interestingly, once you have that forward model, can you extract from it some sort of utility function to then trigger online the sampling decisions that you want to make, right? So I give you a model that predicts the biology. I want to put that through some kind of measurement of utility, and when those utilities spike, I want to trigger these sampling choices. That's kind of the loop. Then you trigger the sampling decisions, you bring water samples back to the lab, they're still analyzed offline, they get labeled, and then you can redo your model. And so that's essentially the workflow. And so the way the problem looks is there's some sort of feature vector, which is a low dimensional thing. It's about 6 things. D is about 6 to 8 things. These are things you can actually measure on the vehicle. There's a training data set that pairs these Z values with these fingerprints that we call B sub I, B for biology. And our model for the organism abundance is just a Gaussian process with a standard squared exponential kernel that essentially predicts what the biology looks like from these measurements Z. So we just do a fit to about 10 years of data. And then the vehicle goes off and makes measurements at some locations based off of some utility function. And I'll tell you in a second what the utility function is. And the overall goal is to maximize this utility in an online fashion. So remember, the labels happen offline, but the utility maximization has to happen online as you're moving around the water, right? So that's the thing. And so the model is fairly simple. It's a Gaussian process. There's a square exponential kernel. Our paper talks a little bit about how you pick the hyperparameters for this kernel. It turns out to be non-trivial to do because these dimensions of these measurements Z are quantities that are very different from each other. Like salinity, there's no common base to convert salinity to nitrate concentration. And so how you pick the lambda values, at what scale these various quantities decorrelate, requires a fairly careful analysis. And it's not something we could do on our own. We had to actually talk to our oceanographer friends who have a good sense for how these quantities decorrelate in the ocean. And so we spent quite a bit of time kind of hand-tuning lambda. We have a follow-on paper that talks about how to do that automatically, but the results I'll show you here were all for kernel parameters that were hand-tuned. But it's a fairly low-dimensional input vector, so it's not unreasonable to try and engineer this. So that's the model. It's fairly straightforward. And so how do you pick a utility function? So this is a classic problem. Many of you have studied sampling, and you're familiar that if you want to put a utility function on a map of some sort that you've built, there are 2 extremes that you can choose between. Right? You can believe that you've built an excellent map, and then all that remains is to maximize the primary mode of the distribution, maximize the mean maybe. This isn't purely what's called an exploitation strategy. Or you could believe that you haven't built a particularly good map, that your training data set is really, really poor. And so you want to build a strategy that causes the model to explore, and so you can do something like maximize the variance. Right? So there was a very nice paper a few years ago that invented a very careful balance between the two. This was from Andreas Krause's group. And this technique is called the GPUCB. So it's particularly for Gaussian processes. This is the Gaussian process upper confidence bound, which is a weighted combination of the mean and the variance of a Gaussian process, right? And so it's precisely this combination. And so our only twist to this is to figure out how to do batch updates in the GPUCB setting. So if you look at our paper, we give an explanation for how you can do this in batch in principle way.